welcome to this video on U-values. It's chapter 16 of the Get Constructive book. This comes from the Leaving Cert Construction Studies. U-values comes from the ability of how, or refers to, should I say, to how well building materials conduct heat. So this goes everything from plaster to insulation to concrete blocks. We look at everything, okay? In Irish legislation, there is a certain amount of U value that each building must hit. Okay, it's a maximum requirement. Can it be lower? Yes. That's what we're going to look at now in a minute. What a U value is? A U value is a measurement of heat transfer of 1 Kelvin through 1 meter squared of a building. Okay, it's important it says meter squared because we're going to have to in the future convert from millimeters to meters. So hence it's really important that we actually look into exactly what we're doing. So let's have a little talk about it. Generally speaking, these are going to be our units of measure. Watts, meters, Kelvin is a unit of temperature. Okay, you can see it there over there on the chart. You can go through this in your own time. I will not be going through it today. The lower the U value, the less heat that is lost through the building. So generally speaking, we want our U value to be as low as possible. An example of this is a passive house standard, which is a U value for a wall of 0.12. Okay, a normal traditional house, a normal wall, the maximum it can be is a 0.21. And that's what we're going to look into. How do we come up with these actual numbers? U values vary according to the following. You have the materials that are used in the building. Every material is slightly different. Building's location, the temperature difference between outside and inside, and so on and so forth. Okay? But what we will look at is we're going to look at the whole environment. Now, according to building regulations in 2011, they are as follows. A roof pitch with horizontal insulation, 0.16, pitch with parallel insulation, 0.16, flat roof, 0.2, wall, 0.2. You also have a floor there of 0.1 or 0.21 as well. And you have a window, door, and roof light at 1.6. Again, the lower the number, the better in this case. BER is a recent assessment or recent figure put on all appliances and buildings. Okay, you'll often see them on the likes of your tumble dryer, washing machine, or fridges. Okay, if you're buying or selling a new house, you'll also see one. It considers the energy used by the building and also the CO2 output. BER, apologies, BER is building energy rating. Okay, so it goes between A to G, and it also very similar has a C1, C2, C3, so on and so forth. It lasts for about 10 years. Every house sold or rented must have this rating. This is to ensure that the customer or the person buying slash renting that's living in the building knows exactly how well insulated the building is, how energy efficient it is. U value calculations, so each material has a different U value, and this is something that we're going to be looking into. They're collected together in a table of thermal conductivity. Basically, every single manufacturer, every single product will have either resistivity or conductivity on them, and it's our job to add them all together and see what this works out at. How this works. This is the terminology we need for calculations. We have conductivity, which is always denoted by a small k, resistivity, small r, thickness in meters, very, very important, your resistance, and your U value itself. So let's go through this. Conductivity, or small k, is referred to 1 over r. So if it does not give us our actual conductivity, we can work it out if we know what the resistivity is. Vice versa, resistivity, small r, we can work that out as 1 over conductivity. Again, this depends on if they've given us the conductivity or resistivity. We only need one or the other. We don't necessarily need both. Thickness measured in meters. Again, we're going to have to convert from any other units like millimeters to meters. You have your resistance there, or, so in this case big R, resistance equals resistivity times thickness, so multiplying. And then you also have resistivity equals thickness divided by conductivity. You also have that included in this. You also have U values there of 1 over RT. RT in this case just stands for total resistance. So that's everything added up together. So where this comes in, it comes in pretty much every single year is question 5. Okay, what we're going to look at, we're not going to go through this, but there are samples continuing out through this PowerPoint. What we are going to do in this video is we're going to have a look at draw the table below as shown for the 2024 exam paper. The table goes as follows. The table I do is I generally go element / material, thickness, conductivity, resistivity, resistance. I like to put my thickness in first just because it helps me read it off. Okay, and that's what we're going to be looking at. So going to the website, you'll notice this PowerPoint is going to be here. This video will be up later, and I may add another video for section B and section C. Those two sections will not be covered in this video. This video is just talking about section A. Now, what we're going to notice is our section A, okay, our question 5 is one of those questions that comes up pretty much every single year. It's not written into the curriculum that it has to be a question 5. Just for the last 20, probably 30 years, question 5 has always been a U-value question of some shape or form. Last year, 2024, it was this concrete block wall, with your insulation, block wall in the middle. Okay? The previous years, it's been floors. Okay? Generally, they will not ask about roofs or doors. Generally, that's speaking just because of the complexity of it. You will or may be asked about a timber frame wall in case that does changes working a little bit. But what we're going to be doing is we're going to be working on what we see here in front of us. So let's open that. So looking through this, I have my question on my right, or my left should I say, and on my table on my right for you to go through with me. Now, generally speaking, I'll always start off with your resistance of internal external surfaces. Now, these are one of those things that are a little bit convoluted. Most people don't fully understand where they're coming from. So let's have a quick discussion and look at that. Now, in terms of our wall, we're going to have an internal leaf. Let's just take a standard block wall for a passive house. So we have our two outer blocks, so our outer leaf, our inner leaf, and my insulation here in the middle. On each of my walls, so both external and internal, I have this very thin layer of air. Believe it or not, that thin layer of air that's actually sitting on top of my blocks, sitting on top of my blockwork, provides a tiny bit of insulation to my building. Okay? And that tiny bit of insulation also has to be covered and accounted for. That's where that resistance of external surface comes into play. So when we're writing that in, we can write this in shorthand. We can write in resistance EX surface. Your examiner will know EX stands for external. Thickness, there is none. There is no physical thickness to that. So you can put a line through it. Same thing with conductivity and resistivity. If you notice in the question, it has the big or, which straight away means that is going over here into my resistance. 0.048. Same thing is going to happen with your acrylic render. Now, what I'm going to do is I go followed by what they have in the diagram. So they have thermal data of external wall. That is what I always follow. If you ensure every single piece of data is in, generally speaking, you ensure every single part of your question is there. So next up on their thing, it's going to say acrylic external render. External render. And this time I do have a measurement. So what I want you to do is have a quick look at A and look at an external acrylic render of 12 millimeters. So 12 millimeters in terms of my meters is going to be at 0.012. You can do this on a calculator, or a very quick way I found to do any of this is add 2 zeros. Okay, so add 2 zeros to the front of it. So what I mean by that is if I want to go along with my external insulation, that's now going to turn into 0.1 What I keep trying to do is I keep working through it. So if I have my number there, generally speaking, if it's a 2-digit number, you can add a 0 on front of it and you have your answer. You generally always add a 0 on front to try and make it a 3-digit number. Internal skim code you see there is at 4 millimeters. I know off the top of my head I need to make that a 3-digit number, so that's going to become 0.004. What I'm going to now do is I'm going to quickly just put a quick pause on this video. I'm going to fill in the table and I'll get back to you when the table's filled in. So, welcome back. Based off the actual diagram, okay, from what we've got, you can see here, I'm just double checking my calculations, filling in, making sure everything is filled in. But double checking exactly what's after going on here, okay, we're after seeing all my values are put in. Here are my values stored into my table. What we have to remember is my conductivity is my division. My resistivity is my multiplication. These both go into my resistance. Okay? Again, remembering your formula. R equals either T, H, I like to call it TH just so it stays the same, but it is thickness, multiplied by little r, or it's R equals TH divided by my K. Okay? So, again, working things out, you can do this easy on a calculator. I'm just going to use the marking scheme to speed things along. So, in this question, 0.018. And now I get down to my total resistance. Okay, in this case, my total resistance is going to be at 7.044. Again, making sure we're going along and using our normal formulas. And also you can add in here our units. If you're unsure what the units are, a very handy trick I learned years ago was or, and you can see the units beside it. So in this case for our or, it's meter squared degrees watts. Okay. Down here again, going through everything. I have my formulas, I have them written down. Again, you get marks for your formulas. Necessarily if you get these incorrect, but if you have your formulas written down, you will still end up getting correct marks for it. Okay? So even if you don't understand how to do this, writing down these formulas will also get you marks on your exam for this. Now, for your U value, okay, that means it's 1 divided by 7.044. That will give you your U value, in this case of 0.142. And again, making sure you're using your units, watts per meter squared degrees. That there is my answer to part A. Okay, this video we're only covering up to part A and we're going through it like we've just done. Okay, this is how you answer part A. Again, conductivity, you're filling it into the formula. This case, dividing by K. Resistivity, you're multiplying by your thickness, and then you're adding them all up. Adding them all up, you'll eventually get to your U value of 0.044. Once you have that, you're then going to go along and do this final last bit of calculation. 1 over total resistance equals your answer, your U value. Please stay tuned for the other videos on part B and C of these questions. Part B is generally finding the calorific value of oil. So how much actual oil, sorry, not the calorific value, the heat loss calculation. So how much heat loss as an actual unit in euro has been lost throughout a year or a given period. That's generally what part B is going to be asking you. Part C over the last number of years has changed. So part C is a bit trickier to nail down, but I will be doing a brief video on that in the future. So for now, that's part A, and I hope this has been helpful.